Okay, folks. So this is a sequence of numbers, and what I'm seeing is a couple of things you want to pay attention to with the sequences. The two big types of sequences that we're gonna work with this term is arithmetic and then geometric. And the arithmetic sequence are just linear functions. The geometric sequences are exponential functions. So, I mean, we could have gone back and done these at those when we did back in chapter 2 and chapter 4. I just didn't. It's fairly straightforward, so we left it to this week now. Okay, so what are some things you got to pay attention to? How can you tell if it's an arithmetic sequence? We'll start with that. Well, what I'm basically seeing is I'm seeing how much is this increasing each time. So I see it went up by 5, went up by 5, went up by 5. So because it's always going up by 5, that means this is an arithmetic sequence. Looks like I'm spelling arithmetic, but it's arithmetic, is how we say it. Kind of like, what is it? Potato. So arithmetic, if I can spell it. And this 5 is called D. It's the common difference. You look up here in these notes, you'll see that. The common difference. And it's what we're adding each time. You used to call it the slope, right? It's the slope still, but here's just a different context. Because that's the common difference. And then what we usually do is we usually have some notation like this. And that usually means a sub 1 means the first term. And then we'll usually say a sub n equals the nth term, whatever term we're looking for. And then you'll see this notation, a sub n minus 1. And that means the last term that we use, the previous. Let me not use the word last. Let me use the word previous. Because I don't want you to get confused with the last term, meaning the very end of it, and previous, AUS, right? Term. And that's really all there is to it. I mean, yeah, then you get all these special, formulas to deal with. So let's talk about some of them. And one of them is right here, the recursive formula. So I can come up with a recursive definition here. Let me erase some of this. Okay, so we know the common difference is 5. And we also know the first term for this sequence is -4. So if I wanted to write a recursive formula, the way you write a recursive formula is you write your first term is -4, and then you say to find the next term, whatever term you want, you're going to take a sub n minus 1 plus the common difference, which in this case is going to be 5. And that's the recursive formula. And this is kind of, I don't know how useful it is, because in order to use it, if I wanted to find the 20th term, I would have to add 5 19 times, right? Because there's the first term. And I don't want to do that. So usually what we'll do is we'll develop, here's a recursive formula, and sometimes recursive formula is all we need. Then we have an explicit formula, which let us automatically jump to a term. So for the explicit formula, the explicit formula, this is not writing that well today. Maybe it's probably me. What we'll do is we write a sub n, so whatever term you want, you take the first term plus the common difference, and if it's negative, you go minus. And then you do n minus 1. So I said if I wanted to find the 20th term, if I want to find a sub 20, instead of having to add on that 5 19 times, you're probably asking, how come I said 19 when I want the 20th term? You're going to see why right now. 20 minus 1. See, we've already got the first term. The first term is -4. So we need 19 more terms to get to the 20th term, right? So -4 plus 5 times 19, what is that? 20 times 5 is 100, so that'll be 95. And 95 minus 4 is going to be 91. So the 20th term is 91. Okay, so that's so far what we've got for an arithmetic sequence. Sometimes you want to find the sum of a set of numbers. So here's a sequence. You know it's the same sequence, and I know this is the 20th term. Okay, so why don't we talk about some things? I know the 20th term. I didn't know that originally, but I found it. And if I asked you to find the sum of the first 20 terms in the sequence, well, we didn't know the 91 was the 20th term. So we had to create that sequence. We had to say a sub n equals, or we even had to say, let's jump ahead here. A sub 20 equals -4 plus 5 times 20 minus 1. And that's where we came up with the 91. Now, in order to find the sum of a arithmetic sequence, it's called a series. What we'll do is we'll take, and you'll see this on this formula next page. You take the first term. Actually, it's written just a little bit different, but it's the same math. I'm going to take the first term plus the last term. See, that's why I wanted to use previous rather than last, over however many terms you have divided by 2. So in this case, I have 20 terms. And I'm going to divide that by 2. And the first term is -4. The last term is 91. So to find out what all the numbers between -4 up to 91 add up to, we just have to do this trick. And what is that? That's 10 times, what is that, 87? So that would be 87, or 870 is what all those numbers add up to. And that's a partial sum, we call it. It's the sum of the 20th terms, yeah, I mean, I guess that's good. Maybe we should do another version of this. So you see with this sequence, and it's a series, and the reason I know this is a series is because they're telling me to add up the numbers, okay? And I don't know how many numbers there are. They didn't tell me. So I got to figure that out, because remember the formula, I know the first number. I know the first number is -1. I know the last number is 151, but I don't know what n is. So I got to figure that out. So since we already have been working with the series, or the sequence, we already know that the explicit formula is a sub n equals -4 plus 5 times n minus 1. And we know a sub n is. We know a sub n is the 151. But what we don't know is n. I don't know how many terms there are. So then we just got to do a little algebra. We're gonna add 4 to both sides. And then you can do some distributing if you want, but I also can just divide both sides by 5. And I think that's 31. So 31 equals n minus 1, so n has to be 32. So that tells me that 151 is a 32nd term. So we just need to drop 32 into there and then go ahead and crunch it the same way. Do the sum and times it by 16. Okay, so that's something that happens. I guess anything else for the arithmetic will let you work on the math exercises, and there might be some in this paper packet if you want to do them too. So here's a second sequence, and since I already told you we're working with geometric and arithmetic sequences, this obviously has to be geometric. So what makes a geometric sequence a geometric sequence? Well, remember how with the arithmetic it went up by the same number? With the geometric sequence, if you take the second number divided by the first number, 2, I get 2. And then the next one be 12 divided by 6, that's also 2. So this tells me that I have to times it by 2 each time to get to the next number. So that's what makes it a geometric sequence. The common ratio, remember how we talk about common difference? So the common ratio in this sequence is 2, because that's what we got when we kept doing all that division. Second number divided by the number divided by the number before, it always came out to be 2, so we know it's geometric. And we know the very first term, and we use A. I've seen some books use G for geometric. We'll just use A to keep it the same. In this case, the very first term is 3. And if I wanted to write a recursive formula for this, well, I would write A sub 1 equals 3. And then to get A sub n, I'd take A sub n minus 1 and times it by 2, because that is the common ratio, right? Take the last number, you multiply by 2. So the next number up here would be 24 times 2. So the next number would be 48. The next number would be 96, so on and so forth. Okay, so that's the recursive version of a geometric sequence. Now and the trouble with this, though, again, as with an arithmetic, you'd have to calculate the one before it to get the next one. It would be nice to come up with an explicit formula and be able to jump right to that. So to jump to that explicit formula, generally what it is, it's written A sub n equals the first term times the common ratio raised to the n minus 1. You always have to do n minus 1, because if you do n equals 1, you want this to be r to the 0, which gives just your first term. So we know the common ratio. We know the initial value here. The first term is 3. And then we know the common ratio is 2 raised to the n minus 1. And that's an explicit formula that lets you jump to the whatever term you want. If I want the 100th term, I only have to do 3 times 2 to the 99th. And if you follow order of operations, 2 to the 99th times it by 3. Big number, we don't want to calculate it. Okay, but you certainly would save you from writing it out. What's this? 1, 2, 3, 4, 5. Would have to do the 5th term times 2, the 6th term times 2, all the way up to the 99th term times 2, which we wouldn't want to do. Okay, so that's how you generate the sequence. In this case, I get. So then we have this series. What's the sum of a arithmetic sequence or a geometric sequence? And you're probably asking, why would I ever use this? Well, paychecks, income tax, not income tax, your pay raises over the year, compound growth, exponential growth. Those are all, and you're adding up the sum of all those terms. So that would be a series in that case. So first off, this formula sheet starts us off with the geometric series, and what these numbers all mean is, well, you recognize the first term, and you common ratio to whatever number of terms you're trying to do over 1 minus common ratio, and then you just do the arithmetic, do the algebra. So for that last sequence, that was 3 and 6 and 12 and ... And we know the common ratio was 2. We know our first term is 3. So what if I wanted to find the sum of the first 3 terms of this geometric series? And it would be a series, because now what we're doing is we're saying 3 plus 6 plus 12. Well, isn't that 8? Let's see, that's 9 plus 12 is 21. So we know the sum of those 3 numbers in 21. I mean, why would we do that? Why would we do anything more than that for this? But what happens if it's the first 30 terms or the first 300 terms? Then you need another technique. And that's why we're going to do learn that other technique. So the formula says, take your first term, times by 1 minus your common ratio, raised to however many terms you want, all over 1 minus your common ratio. And then you're just going to follow order of operations. That's going to be 3 times, let's see, 2 to the third is 8. 1 minus 8 is negative 7. And that's going to be divided by 1 minus 2 is negative 1. The negatives cancel out. 3 times 7 is 21. Okay, and that's what the formula is. You take, I guess I could do another example, but it's all the same kind of thing. You do the raise the common ratio to however many terms you're trying to add up, and not n minus 1. That's how you generate the sequence. Here we're trying to find the series over 1 minus r. Okay, so that's for a partial sum of a geometric sequence. And maybe before I do the next one, I should talk about an infinite sum. So for an infinite sum, what we're going to see is you're going to usually see this in terms of this sigma notation. They usually start something like this. They start showing k equals 1. You could do n. I mean, really, the letters don't really matter. n equals 1 to infinity is what we'll sometimes see. So we want all the terms of, and then they're going to give us some kind of sequence like 3 times 1/2 raised to the n minus 1. Well, let's see. I don't know what kind of sequence this is. You probably know it's a geometric since I'm talking about it. But what are some features about this that lets me know it's going to have a sum? Well, what's my first term? My first term is going to be 3 times 1/2 to the 1 minus 1. Well, isn't that 3 times 1? Because 1/2 to the 0. So the first term is 3. Of course, we kind of saw that there. The next term is going to be 3 times 1/2 to the 2 minus 1. So that's going to be 3 times 1/2. So that's 1.5. Hopefully, what are you noticing about these numbers? The next one is going to be 3 times 1/4, right? Which will be 0.75, 3/4. What are you noticing about these numbers? I hope you say, no, they're going down, they're decreasing. And that's right. So when my common ratio is less than 1, between 0 and 1, it could be negative too. I guess you could say between, well, I guess I'm going out on a limb saying this. If your common ratio is between -1 and +1, what's going to happen is the sequence is going to become smaller and smaller and smaller. In the case of r is negative, it's going to bounce back and forth between positive and negatives. But either way, it's going to get closer and closer and closer to 0. This is going to converge. It'll converge on a value, and if it'll converge on a value, you can find the infinite sum. So you guys, what if you guys walk up to me and say, Mr. LeMay, I want a soda? And the next one I give it to you, the next person walks up and said, Mr. LeMay, I want a half a soda. And the next one walks up and says, I want a quarter of a soda. And the next one says, I want an eighth of a soda. And so on and so forth. What have an infinite number of you come up and ask me that? Well, how much soda do I need to satisfy your thirst? Well, what we need to do is, what you want to think about is this is really an infinite geometric series, because what's happening is each time I start with 1 soda, and each of you want half of the previous amount. So this goes from n equals 1 to an infinite number of you. So will this ever come to a value? Well, we know the common ratio between -1 and 1. So the yes is going to, that each amount gets, I start with 1 soda, then I start with a half a soda, then I go to a quarter of a soda, and I go to the eighth of a soda, and so on and so forth. Those amounts are getting smaller and smaller and smaller. They're going to eventually get almost 0. So how many sodas do I need? Well, you take, here, I don't think I have that formula here, so I'm going to give it to you. You take your first term, divided by 1 minus the common ratio. This is the sum of an infinite, let me spell it right, infinite geometric series. So the first term in this case with the soda is 1 over 1 minus the common ratio, which is a half, because I'm always giving you half as much. So what's 1 divided by 1/2? Isn't that 2? So I'll need 2 sodas. I'll need 2. And that's how these infinite geometric series work. As long as your common ratio is less than 1, or between -1 and +1, usually they're going to be positive. So I wouldn't worry too much about it if it's negative. But it will work if it's negative, as long as it's like -1/2. And you find in a series. You find in the series, you're adding them up. So I guess that's that. So I guess the only other thing, and I might have done some of this already. I made the rest of this video about a week ago, so I don't remember. But I'll walk you through this next formula too. Okay, this next formula looks kind of gnarly because they're giving me 2 forms of it. It's the same thing. This is just generating a sequence, and I wouldn't worry too much about it. I would tackle it this way. And what does that formula say? That says take your number of terms, divide them by 2. I'm just doing a little bit of distributive property. Then you take the first term plus the last term. Add those together, times by n over 2. So if I want to find the sum of the first, common, something pops up a lot on the SATs kind of thing. What if I want to find the sum of the first of the first 100 even numbers? Well, there's 100 of them, and the first even number is 2. What's the last even number? I mean, at least on the first, isn't that 200? So it's going to be 100 over 2 times 202. Isn't that 100 times 101? So that's what? 10100. So that's what the first sum of the first 100 even numbers add up to. And it's that easy. And now, if they tell you to find it like in a sequence, if they tell you some kind of sigma notation thing, here, let me stop this and erase it for a minute. So what if they give me this sequence and they tell me to find the sum of the first 50 numbers? Well, I certainly don't want to write down 50 numbers and add them up. So we're going to use this method here. I'm seeing, first up, I got to decide, is this geometric or arithmetic? Of course, you know it's arithmetic because that's the formula we're using. But what if you didn't? I see that this is increasing by 4, this is increasing by 4, this is increasing by 4. So I see it's an arithmetic sequence. The common ratio is 4. I know the first term is 3. I know the 50th term is going to be 3 plus 4 times 49, right? 50 minus 1. So 3 plus 4 times 49. I got my calculator right here so I don't make a mistake. Let's see, 4 times 49 is 196 plus 3 is 199. So now what's the sum of all those numbers? Well, we have 50 numbers divided by 2 times the first term, which is 3, times the last term, which is 190, or plus the last term, which is 199. And we'll do that. 3 plus 199 is 202. And then I'm going to times that by 50, right? Because 50 divided by 2 is, or times it by 25, I mean. Because 50 divided by 2 is 25. So that adds up to the number 5050. And that's how that works. See what all this is doing. Maybe we should talk about what's going on here with that formula. Maybe you see what's going on with that formula. Let's just clean this up for a minute. So you see when we write this formula out, this is the first term. This is the arithmetic sequence that generates the term. So for this last question, if I had done that, it would have been 3 plus 3 plus 4 times n minus 1, and then we could just do a little bit of algebra here. A sub 1 plus a sub 1 is 2 times a sub 1, or 6, plus 4 times, 100 minus 1. So you see where they're doing that 2 a sub 1s from? It comes from those 2 a sub 1s. This is just, I wouldn't bother learning that. I would just remember this one, first term plus last term. Okay? Let me go and see what else I got, if I've missed anything, and then I'll make this video end.